Military equipment from World War II sits in museums and barns across the world, and something about these machines makes no sense. Aircraft built 80 years ago still wear their original primer with zero corrosion beneath it. While modern cars develop rust spots within a decade, tanks, abandoned in fields for generations, show original paint holding strong on protected surfaces. Yet brand new equipment requires constant repainting just to stay functional. This is not nostalgia or selective memory. The paint formulas used during World War II actually protected metal better than almost anything manufactured today. These coatings contained ingredients now banned or heavily restricted. And when regulations forced manufacturers to reformulate, protections suffered dramatically. The chemistry that made wartime coatings exceptional still exists in the scientific literature. And understanding why it worked reveals exactly what modern alternatives sacrificed for safety and convenience. Number 1. The ultimate test. World War II created a paint engineering challenge unlike anything before or since. Military equipment had to function in every climate on Earth simultaneously. And paint failure meant mission failure, equipment loss, and dead soldiers. There was no room for coatings that worked adequately. Only formulations providing absolute protection could meet wartime demands. Consider the environments these coatings faced. Naval vessels operated in salt water that corrodes unprotected steel within weeks. Aircraft carriers and battleships required coatings that survived constant salt spray, tropical humidity, and Arctic cold during the same deployment. Aircraft flew through temperature ranges spanning over 100 degrees in a single mission, climbing from hot runways into freezing high altitudes. The thermal expansion and contraction that occurred during every flight would crack inferior coatings within months. Ground vehicles faced different but equally severe challenges. Tanks in North Africa endured temperatures exceeding 120 degrees while sand blasted every exposed surface. The same vehicle designs operating on the Russian front faced temperatures 40 degrees below zero, where metal becomes brittle and paint adhesion fails under thermal stress. Beyond environmental extremes, military equipment faced chemical exposure that destroys most coatings. Aviation fuel, hydraulic fluid, lubricating oils, and cleaning solvents contacted painted surfaces constantly. Any coating that softened, dissolved, or lifted under chemical exposure failed immediately and required field replacement under combat conditions. The production scale made durability essential rather than optional. The United States alone produced approximately 300,000 aircraft during the war years, over 88,000 tanks, and nearly 7,000 naval vessels. Millions of trucks, jeeps, artillery pieces, and support equipment rolled off production lines requiring protective coatings. Repainting this equipment in the field consumed resources desperately needed elsewhere, and coatings that lasted reduced the logistical burden dramatically. Number 2. Zinc Chromate. The self-healing primer. Open any preserved World War II aircraft and you encounter a distinctive yellow-green coating covering nearly every aluminum surface. This Zinc Chromate Primer remains visible after 80 years because it works through a mechanism that modern primers cannot replicate. And that mechanism explains why nothing since has matched its protective capability. Zinc Chromate Primer does not simply cover metal and block moisture like modern coatings. Instead, it creates an active chemical barrier that continuously protects the underlying aluminum. When moisture reaches the primer surface, the chromate ions dissolve slightly and migrate toward any exposed metal. This migration means scratches, chips, and minor damage receive protection from surrounding intact coating rather than becoming corrosion starting points. Scientists call this self-healing protection. And the difference between self-healing and barrier-only primers explains. Most durability comparisons between wartime and modern coatings. A modern primer protects metal only where the coating remains intact. Once scratched or chipped, the exposed metal begins corroding immediately with nothing to stop the process. Zinc Chromate continues protecting damaged areas by chemically migrating toward exposed surfaces. Beyond self-healing properties, zinc chromate bonds chemically with aluminum rather than just adhering mechanically. The chromate ions react with the aluminum oxide layer that forms naturally on aluminum surfaces, creating a connection at the molecular level. This chemical bond means the primer becomes part of the metal rather than sitting on top, waiting for moisture to work beneath it. Aircraft restorers encountered this durability constantly. Original zinc chromate primer from the 1940s often remains more firmly attached and more protective than replacement coatings applied decades later using modern formulations. The original coating penetrated into the aluminum surface and formed chemical bonds that modern alternatives cannot achieve. The armor that never quit. Steel and iron required different protection than aluminum, and World War II engineers relied on red lead primer for virtually every ferrous metal application. This distinctive red runge coating covered ship hulls, tank bodies, bridge structures, and every piece of steel equipment that required long-term corrosion resistance. Surviving examples demonstrate why nothing manufactured provides equivalent protection. Red lead primer works through a combination of mechanisms that modern alternatives only partially replicate. The lead oxide particles create an extremely dense barrier that moisture penetrates slowly, if at all. Unlike porous modern primers that allow water vapor transmission, red lead forms an almost impermeable layer between steel and the environment. More importantly, red lead reacts chemically with the steel surface to form lead soaps, compounds that stabilize the steel and resist corrosion initiation. This chemical reaction means the primer integrates with the metal rather than simply coating it. Once established, this bond persists for decades without degradation under normal conditions. Red lead also demonstrates self-healing properties, similar to zinc chromate, though through different chemistry. When damaged, the lead compounds around the damaged area react with moisture and steel to form protective compounds over exposed metal. Minor scratches and chips seal themselves rather than becoming corrosion spreading points. Naval applications demonstrated red lead durability most dramatically. Ship hulls coated with red lead primer systems during World War II often required minimal maintenance for decades after the war ended. Modern coatings on the same vessels require reapplication every few years to prevent corrosion breakthrough. Lead toxicity ended widespread red lead use. The neurological damage lead causes, particularly in children, made continued use unacceptable once the health effects became fully understood. Residential lead paint was banned in the United States in 1968, and industrial applications faced progressive restrictions afterward. Number 4. Oil-based paints. Modern paints dry through evaporation. Water or solvent leaves the coating, and what remains forms the protective film. World War II paints worked differently, and that difference explains much of their superior durability. Oil-based formulations using linseed oil as the primary binder cured through oxidation, a chemical process that continued strengthening the coating for months after application. Linseed oil absorbs oxygen from the air and transforms into a solid polymer through a process that takes weeks to complete. During this extended curing period, the coating continues hardening, cross-linking, and bonding more thoroughly to the underlying surface. A linseed oil paint reaches maximum hardness and durability long after it feels dry to the touch. This slow curing process created coatings fundamentally different from modern fast-drying alternatives. Oil-based paints applied during World War II had time to flow into every microscopic surface irregularity, penetrate into the primer layer beneath them, and form films of exceptional uniformity. The resulting coatings bonded mechanically and chemically at levels modern water-based paints never achieve. Flexibility combined with this hardness to create coatings that moved with the metal rather than cracking under stress. Temperature changes cause metal to expand and contract continuously, and rigid coatings crack under this constant movement. Linseed oil films remain slightly flexible throughout their service life, accommodating dimensional changes without losing adhesion or protective capability. Application methods reinforced these advantages. Brush application was standard practice for critical equipment, and brushing works paint into surface textures more thoroughly than spraying. The physical action of brushing forced coating material into contact with the substrate at a level spray. Application cannot replicate. Modern environmental regulations essentially eliminated traditional oil-based formulations. The volatile organic compounds released during drying contribute to air pollution and respiratory problems, and regulations progressively limited VOC content until traditional formulations became impossible to manufacture legally for most applications. The coatings that replace them dry faster and emit less pollution, but provide measurably less protection over extended time periods. Number 5. Why modern coatings fail the comparison. Understanding why World War II paints outperformed modern alternatives requires examining what changed and why. For fundamental shifts in coating technology explain the durability gap, and none of these shifts prioritized protection. The first shift replaced active corrosion inhibition with passive barrier protection. Wartime primers containing zinc, chromate, and red lead actively protected metal through chemical mechanisms that continued working even when coatings suffered damage. Modern primers primarily work as barriers, blocking moisture from reaching metal surfaces. Once breached, modern primers offer no secondary protection, while wartime primers continued protecting damaged areas. The second shift replaced penetrating oil-based binders with surface-sitting water-based acrylics. Linseed oil formulations soaked into substrate surfaces and formed bonds at the molecular level. Water-based paints sit on surfaces and rely on mechanical adhesion to surface texture. Moisture works beneath water-based coatings more easily. And once moisture reaches the interface between coating and metal, adhesion fails progressively. The third shift prioritized drying speed over curing strength. Traditional oil paints required days between coats and weeks to reach full hardness. Modern production schedules cannot accommodate these timelines, so fast-drying formulations replaced slow-curing ones. The chemical cross-linking that made oil-based films so durable requires time that modern formulations do not provide. The fourth shift reduced film thickness to save material and speed production. Wartime specifications called for multiple heavy coats of primer and finish paint, often totaling 15 to 20 mils when complete. Modern single-coat systems and thin film technologies reduce material consumption, but provide less absolute barrier protection. None of these shifts occurred because manufacturers discovered better protection methods. Each shift occurred because regulations, economics, or market demands prioritized factors other than durability. Modern coatings are safer to apply, faster to dry, easier to clean up, and less damaging to air quality. These are genuine improvements in important areas. Number 6. The evidence sitting in museums and barns claims about coating durability require evidence, and World War II provides evidence that no laboratory test could replicate. Thousands of aircraft, vehicles, and vessels from that era survive with original coatings intact, and their condition after 8 decades proves what wartime formulations achieved. Aircraft preserved in museums across the world display original zinc chromate primer on interior surfaces that have never required recoating. Restorers. Opening inspection panels find primer applied in 1943, protecting aluminum as effectively as it did on delivery day. The self-healing chemistry that made zinc chromate exceptional continues functioning after 80 years with no maintenance whatsoever. Barn-find aircraft tell an even more compelling story. Planes stored in agricultural buildings for decades without climate control, without cleaning, and without any maintenance retain original primer in better condition than modern coatings, survive with regular maintenance. These uncontrolled storage conditions would destroy modern primer systems within years, yet wartime chromate primers remain intact. Military vehicle collections provide similar evidence across different substrates. Original olive drab paint on World War II Jeeps and trucks survives on protected surfaces after 80 years of aging. Comparison with modern military vehicle coatings requiring regular repainting demonstrates the durability gap clearly. Museum ships require the most dramatic maintenance comparisons. Vessels preserved with modern coating systems need continuous paint maintenance. Every few years, sections require stripping and recoating as modern paints fail under maritime conditions. Original protected areas coated with red lead primer systems during construction remain stable with minimal intervention. Restoration specialists have documented these comparisons extensively. Professional restorers working with original materials consistently note that wartime coatings outperform modern replacements by significant margins. Original paint often remains more firmly adhered than coatings applied decades later using contemporary products. Number 7. What this means for protection today. Understanding why World War II coatings worked better than modern alternatives creates practical questions about protection options available today. The formulations that provided exceptional durability contained hazardous ingredients that regulations now restrict or prohibit. However, the principles behind their performance remain applicable. Certain specialty coatings still incorporate chromate chemistry for applications where maximum protection justifies strict safety controls. Aerospace maintenance and military applications continue using chromate primers with appropriate worker protection. Because acceptable alternatives do not exist for critical applications, these coatings remain available through specialized suppliers for those with legitimate needs and proper handling capability. For general applications, understanding wartime coating principles guides product selection even among modern alternatives. Penetrating primers that soak into substrates provide better adhesion than surface-sitting products. Oil-modified formulations, where still available, offer better durability than pure water-based alternatives. Thicker film builds and multiple coat systems outperform single-coat applications regardless of product type. Surface preparation matters more with modern coatings than it did with wartime formulations. Self-healing primers compensated for imperfect preparation by protecting areas that preparation missed. Modern barrier-only primers fail at any point where preparation was inadequate. Investing additional effort in surface cleaning and profiling compensates partially for what modern chemistry lacks. Maintenance schedules must acknowledge modern coating limitations honestly. Planning for recoating every 5 to 10 years accepts reality rather than hoping for durability that modern formulations rarely deliver. Budgeting for maintenance prevents the deferred maintenance that leads to substrate damage when coatings fail and remain unaddressed. The fundamental lesson involves trade-off awareness. Society chose safer, faster, cleaner coatings over maximum durability. These choices reflected legitimate priorities and produced genuine improvements in worker health, air quality, and application convenience. However, those choices also produced coatings that protect metal less effectively and require replacement more frequently. World War II paint formulas protected metal better than modern coatings because protection was the only priority that mattered. Zinc Chromate Primers healed themselves when damaged. Red lead primers bonded chemically with steel and blocked moisture completely. Oil-based paints penetrated into surfaces and cured into films that strengthened for months after application. Every element of these coating systems prioritized durability over convenience, safety, or cost. Modern coatings abandon these formulations for legitimate reasons. Lead causes permanent neurological damage. Hexavalent chromium causes cancer. High VOC emissions harm air quality and worker health. Regulations that restricted hazardous ingredients reflected genuine concern. For human welfare and environmental protection, however, protection suffered when chemistry changed. Self-healing primers became barrier-only primers. Penetrating oils became surface-sitting acrylics. Slow-curing films became fast-drying coatings. Each change traded durability for something else. The equipment sitting in museums proves what was lost. Original coatings from 1943 protecting metal better than modern alternatives applied. Decades later tells a story that chemistry explains and evidence confirms. Understanding that story helps set realistic expectations for the coatings available today and reveals why nothing manufactured since quite matches what wartime necessity produced.